Hello, everyone, and welcome to a new edition of the virtual seminar on geometry with symmetries. So today it's my great pleasure to welcome Haotian Wu from the University of Sydney here in Australia, and he'll be presenting on the asymptotic behavior on unstable perturbations of the Fubini study metric in Ricci flow. Thanks, Haotian.
Thank you, Ramiro, for the invitation and the introduction. And nice meeting you, everyone, online. Hopefully, I will meet you in person as well in the future. So, I will discuss some result joint with my collaborators. Let me write their name down. David Garfinkle. So, joint. Jim Isenberg and Dan Knopf. So the talk is about Ricci flow. So let's just begin, right? So we will be considering in this talk only closed Riemannian manifolds of real dimension 2 or higher, right? So compact without boundary. And Hamilton's Ricci flow is basically the following PDE, which says I have a one-parameter family of Riemannian metrics on a manifold, and I want to evolve in the direction of -2 times the Ricci curvature tensor, right? And we know in local coordinates, we can write the components Rij, right? The Ricci components of Ricci as the Laplace of the ijth component plus some lower order terms, depending on the inverse of the metric and the first derivatives, right? So because of this, we know this equation is morally a heat equation, kind of a PDE. However, because this equation also is geometric, right? The diffeomorphism invariance of this equation, in fact, implies your equation is not exactly strongly parabolic. But what one typically can do is you can apply a so-called a de Turk flow, which essentially you can fix a gauge, and then you can turn this PDE into a strictly parabolic system of reaction and diffusion type. And then you can then apply the PDE theory to conclude short-time existence and uniqueness of the flow. Let's say we are on the compact manifolds. All right, so this is the general setup. And since Hamilton's introduction of this flow in the 1980s, right, we know this flow has grown into a major research area in geometric analysis. Now, okay, so if you have any questions, just feel free to stop me and ask. Okay, thank you. Then, of course, now let us look at the most basic example in Ricci flow, which is the so-called shrinking round sphere, right? So I denote a topological sphere by Sn, and this G with subscript round is just the standard round sphere, which we know is Einstein, namely Ricci is a multiple of the metric tensor. And for the n-dimensional, right, for the round sphere, the constant lambda is n-1. And because the sphere is highly symmetric, right? So it's not hard to imagine. For example, you can just consider the two-dimensional case. Then under the Ricci flow, this sphere will shrink, right? Uniformly in all the directions. And this means the symmetry would reduce the Ricci flow PDE into an ODE on the radius, right? If we just call this time-dependent radius r as a function of t. And this ODE is precisely like this. And if we just impose some initial positive radius, then we can just solve it precisely, right? So the radius as a function of t is some constant multiplied by this square root of capital T minus little t, right? This is some finite number. So basically, this example of round shrinking sphere or shrinking round sphere says that under Ricci flow, the sphere will shrink to a point in finite time, right? As little t approaches capital T. Now, this example is nice. Well, partly because you can understand everything about it. But it also raises two sort of deep questions. One is, in general, how do various curvature quantities uh, change along the Ricci flow, right? I mean, because curvatures are sort of morally derivatives of the metric, you can think of these as sort of what are the estimates or higher order estimates for my flow PDE. And also, if you think about the example of a sphere, right, in finite time going down to a point, then you can ask, I mean, like, how do you make sense of this process of something becoming a point, right? So this raises the question is, what does it look like if we can zoom in a certain sense? And of course, to answer these questions, right, the first question can be answered by studying how curvature evolves. Actually, yeah, the curvature evolution equations. And the second one is has to do with this so-called blow-up analysis, right? So this is sort of I guess, a universal idea in nonlinear PDEs. Okay, and of course, in the process, we'll see something special known as Ricci solitons. Okay, so maybe I will try to highlight the things are more important for this talk. Now, um, first of all, let's look at how the curvatures evolve. So, in this talk, we'll be only considering finite time singularities, right? So, suppose we have a Ricci flow solution that exists up to a maximal time interval, smooth, right? So here we mean smooth, and this maximal time is finite. Then a necessary condition is curvature here, right? This is the Riemann curvature tensor. We take its norm with respect to the moving metric. This size of the curvature must have becoming unbounded. Okay. And in this case, we say Ricci flow has a finite time singularity. Now, what we can derive is that if we compute the evolution of the square norm of the Riemann curvature tensor, right? Then, and if I think of this as function u, right? Then this is saying the norm squared is a subsolution to a PDE of this form. 3 on 2, right? So then we are on a compact manifold. We are on a compact manifold with a boundary. We can apply the maximum principle and so on. So the point is that as long as we discuss finite time singularities, there is a very natural lower bound for this quantity. I mean, or the square root of u, which is 1 over the time remaining. Now, if we also impose a similar upper bound, then, right, so this is an assumption, and you might also just strengthen this assumption by using this, right? This symbol just means this and that, right? Basically bounded on the order from below and above by this quantity. So basically, so in this talk, we'll be primarily concerned with so-called type 1 singularities. These are the singularities where the maximal curvature blows up on the rate at the rate 1 over time remaining. Okay. Now, then what? Now, of course, if we go back to this very basic example of the sphere, it's not too hard to see. From the radius, you can deduce how the Riemann curvature tensor evolves, and the shrinking round sphere is an example of a type 1 singularity. Okay, so that's just this one extra word, or yeah, this extra terminology we introduce. Now, what does this type 1 singularity look like as we approach the singular time capital T? For the sphere, it's not too hard to imagine because it's shrinking homothetically, right? You can always just rescale to be let's say a sphere of radius 1. More generally, we will need something called the blow-up analysis, and here is a very rough sketch of what it means, right? Essentially, it's kind of a zooming magnification process. Now, suppose we have a finite time singularity in Ricci flow, and then that means we can pick a sequence of space-time points along which the curvature blows up and the time approaching the singular time, right? And we're going to use this curvature size, just call that ki, as a way to rescale the metric. In a sense, we multiply time by 100 and multiply by space by 10. Yeah, and then we will get from the Ricci flow solution a family of dilated, right, metrics using the parabolic dilation, right? This is coming from the PDE. And then if we can prove certain compactness theorem, and typically this is done by proving the curvature bounds. And for example, in low dimensions, if you can prove the non-local collapsing, right? That's one of Perlman's breakthrough. And then you can then say you can deduce in a suitable sense a subsequence that converging to a limiting geometry, right? So here the precise notion of convergence will be pointed Cheeger-Gromov convergence. But the essential thing is I want to say there's a sort of a compactness machinery that allows you to get a limit known as the singularity model. And in this sort of trivial example of a shrinking sphere, the singularity model would be still itself a round sphere. And of course, maybe here is a good place to put another sort of extreme example, but also you might have seen the picture, right? So suppose on a three sphere, I have a sort of neck pinch, or initially a dumbbell, and then later on, either you can construct, for example, rotationally symmetric examples where this neck shrinks in, so pinches off. Okay. And in this case, maybe if I try to, we're zooming in the middle part, you will see this is modeled by a cylinder, right? So this will be a different example compared to the shrinking round sphere. Okay. Okay. Yep. Okay. And both the cylinders, here we put the product metric with the standard round and yep, and also the round sphere. There are special cases of Ricci solitons. So let me now just introduce this idea of Ricci soliton. What do I mean by that, right? So it is a quadruple. So we have the manifold, the metric, some constant, and a vector field on the manifold, right? And if this thing is a Ricci soliton, if it satisfies this elliptic PDE, okay. So here, so my sign convention might not be the same as some of the papers in the literature, but for us in the talk we'll be looking at so-called shrinking Ricci soliton, which has say lambda is -1. Right, and this is just some derivative term. As an example, right, for the round sphere example, lambda is this number, and we don't need to impose any derivative term. So Ricci soliton in this sense is a more generalized notion of Einstein metric. And of course, they so they're not interesting not only because they generalize Einstein metrics, but also they show up and as the singularity models for Ricci flow, right? For example, in real dimension 4, which is the dimension we will focus on in this talk, our neighbor showed, right, in 2010, if you have type 1 singularities in Ricci flow and you blow them up, then they are in fact Ricci solitons, right? In fact, I think they're even better. They're gradient Ricci solitons, namely the vector field x is the gradient of some function. Okay, so this sort of this slide, the main point is to say, yeah, we have this very special class of manifolds. Okay, so sorry, yeah, and as in the context of Ricci flow. Okay, so they also, right? So earlier we said Ricci soliton itself is on an elliptic PDE. So how are they related to the Ricci flow? Well, it's not too difficult because suppose I have a Ricci soliton, then up to a scaling and a diffeomorphism, we can use the Ricci soliton to generate a solution to the Ricci flow. Okay, so in other words, if you consider all the Riemannian manifolds, I mean, sorry, on a fixed manifold, consider all the possible Riemannian metrics on this manifold, and if you choose to mod out the diffeomorphism and the scaling, then the solitons can be thought as the fixed points of a Ricci flow, right? So now we sort of want to look at this more like a dynamical system problem. And if you see it as a sort of a dynamical system, then it is, I guess, quite natural to consider notions of stability and so on. So the first one is the idea of a dynamical stability. So what do I mean by that? So let me try to draw a picture here, right? Suppose I have some soliton G naught, and I have some very big, I don't know, not big, but let's say some neighborhood. Yeah, sorry, not big. If for every neighborhood V, there is some neighborhood U such that if I start from somewhere here, maybe I flow back to this soliton, or maybe I have here, and maybe I flow back to some other guy in the neighborhood, right? So somehow this is not quite the I guess the typical sort of strong notion of a dynamical stability. In a sense, you always flow back to your fixed point. And also, so here I have sort of two, I guess, remarks or footnote, right? And also, we don't quite consider the Ricci flow itself. Okay, so what we really consider is the following, right? So we consider, so this is the Ricci flow, but then only Ricci flat metrics will be the fixed points, right? But then we can just do a modification, and this brings us to so-called curvature normalized Ricci flow, right? So if I rewrite Ricci flow like this, then all the Ricci solitons will be fixed points. And then you can, for example, linearize this equation at a soliton, or you can also consider the dynamical stability and so on, right? So the first thing remark is in this definition of the dynamical stability, we'll be looking at sort of suitably modified Ricci flow. And also the second case is to illustrate sort of these two, I guess, these two pictures here. So in the nicer situations, all the metrics nearby a dynamically stable soliton will flow back to this soliton. But sometimes the soliton itself comes in families. So here's an example, right? So 4D, so 4D here is real dimension 4, Calabi Yau, K3. So these are Ricci flat, but non-flat. And in fact, there is a sort of 59 dimension of such metrics. And if you pick one of them, you perturb, then the Ricci flow will flow back to one of the guys in this family. Okay, so there's some subtlety in the dynamical system notion. And then if
Sorry, Haotian,
we
could
yeah,
you
sorry, yeah,
make
yeah,
precise? So you say you're on the K3 surface.
yeah.
Um, so the claim is are these steady solitons?
On K3, you will be just looking at this Ricci flow equation. And
Yes.
for example, and these are also compact. You can, for example, linearize the Ricci flow equation and study the Lichner-Rivets Laplacian. And then you'll realize this Laplacian has zero eigenvalues, which corresponds to some kind of a center manifold of finite dimension, which
Of course,
corresponds
but I
to
mean
these
these are
guys.
all
Yeah, yeah,
fixed
yeah.
points, right?
These are all fixed points. Yeah.
So you don't really leave the point. I mean, you start there and yeah, of course you're gonna have a
Oh no no
center
no no!
manifold, but it's just
But if you go but you pick one of these, you perturb, you can leave the space, right?
so this 59 dimension, that's not the moduli space of Ricci flat, Keller Ricci. No, right? That's
I
the
think it
dimension is
is.
much lower. Ah, is it? Okay.
I think it is. Yeah, yeah. For the real dimension 4 case at least. Yeah, yeah,
All right.
yeah, yeah, yeah,
But I mean, if you start on a Ricci flat metric,
yeah.
you're not gonna move on the Ricci flow.
Oh, no, no, no! You perturb a nearby one. I mean, the nearby is
Ah, so
not
you
necessarily
perturb
Ricci
in
flat.
the
Yeah,
in
yeah,
the
yeah, yeah,
okay.
yeah. Maybe I wasn't too precise. Yeah, like a
So
neighborhood, right?
other
So this dot
these
the,
are
like
sta so
yeah.
even okay, okay. Sorry,
Yeah,
sorry,
yeah, yeah.
sorry.
Sorry,
Yes.
sorry, sorry. Yeah, yeah, yeah. Yeah,
They are all they
my
are all dynamically stable, so to speak.
yes, yeah, yeah, yeah. But in a sort of there's a family of such
Sure.
steady guys. Yeah, yeah,
Right.
yeah, yeah,
Right.
yeah. No, no, no. Yeah,
But the 59 dimension is a Ricci flat, guys. Yeah. Yeah.
yeah. I think there's some reference for that. Yeah, I
And the
don't fully
perturbations,
understand
do they
this.
have to be Keller? Ah,
Not in this sense, no, because this goes back to I think
can
like
perturb away from
whereby
Keller.
yeah, you can go away from the Keller in this
Oh, okay.
case. Yeah,
Okay.
yeah, yeah.
Okay,
Okay.
thanks.
Yeah, no problem. Yeah, thank you. Yeah. Yep. And yeah, so again, let me sort of emphasize. So the dynamical stability here really is I have a fixed point. I look for the guys nearby. The nearby is when need not be fixed point, but somehow close in certain sense, right? Maybe you impose certain topology on a space of metrics, or maybe they are close in the sense you can impose some kind of a topology, like um, how do I make sense of this? Like you can say my components of the matrix are closed in the CK sense, something like that, right? If you're on a compact manifold. So with this notion, uh, maybe if we just go back to the sort of the example we saw in the beginning, the round sphere, then the round sphere is also dynamically stable. Now, this time under slightly different Ricci flow, we can normalize the volume. Um, all we are saying is I pick yeah, let me just draw a picture again. So here's G round, and there is some kind of neighborhood nearby. And if you go from here, you'll flow back. Here's a sketch, right? So this is a bit better than the Ricci flat case we saw earlier. And of course, these are proven by some classical results in Ricci flow. One is the first one by Hamilton. Now, if my nearby is measured in terms of a Ricci positive, then it'll flow back. And in dimension 4 higher, then we have this result of Berman-Wilking, right? If you impose the two positive Riemann curvature operator, so the lowest two eigenvalues, if I remember correctly, lambda 1 plus lambda 2 is positive, right? So in both cases, the Ricci flow will flow the metric to a metric of constant sectional curvature. Okay. Uh, Here we don't have this finite t anymore because we normalize the volume. Yeah. So we normalize the time as well. Okay. Yeah. And another notion in terms of stability is sometimes you can impose a sort of a functional, right? So here I'll just review the sort of a classical notion uh, for the yeah the Einstein matrix. So if we have the Hilbert-Einstein functional, then we compute its Euler-Lagrange equations. Then that is precisely the Einstein metric. Okay. Now, um, because Ricci solitons are generalized Einstein metrics, right? You can ask whether there's also a variational structure for the Ricci solitons. The answer is yes, and this is given by one of Perlman's breakthroughs, namely, sure. So the quick answer is yes, there is a variational structure. So Perlman defined this W functional, and then associated with that, there's a sort of so-called shrinker entropy nu defined like this. The important thing is if you can compute the first variation of the shrinker entropy nu, these are given precisely by the gradient shrinking Ricci solitons. And in particular, right, Perlman showed that along Ricci flow, this shrinker entropy nu is strictly increasing, right, except on gradient shrinking Ricci solitons. So this gives you a sort of a variational. So well, we have some kind of functionals, right, defined on the metrics, and you can then do calculus variation. And then this brings us to this, I guess, concept of so-called variational stability. So we say a soliton is variationally stable if the second variation of this new guy is non-positive. And some people will choose to call this linear stability. Okay. It really depends on the paper. Like for example, I think in this paper by Huaidong Cao, Hamilton, and Ilmanen, they call this linear stability. Yeah. But in this talk, I'm going to call them variation. And if we are considered compact Ricci solitons, then dynamical stability would imply variational stability. So somehow these notions are related. And of course, if you can show variational instability, then that would imply dynamical instability as well, right? So, and in fact, this is kind of relevant because for our talk today, we'll be looking at CP2 with Fubini studi. And of course, in general, right, if m is greater or equal to 2, here's a complex dimension, then if we put the Fubini studi metric on this manifold, this is okay, it is Kähler, but it's also Einstein, and this is a constant. Now I think for many years people thought this guy is dynamically stable under Ricci flow, but Kröncke showed that no, he considered third derivative of the Perlman shrinker entropy. Basically, he showed that this CPM with Fubini studi is not a local maximum. So it's more like a sort of point to inflection. And then, therefore, it's not dynamically stable under Ricci flow. Okay? And there are sort of two important remarks associated with his proof or this result is maybe I should, okay, I'll keep this order, yeah. So the first is these unstable perturbations, they are conformal, and the perturbed metrics are no longer Kähler. Okay, so somehow this is it is sort of weak because there are certain directions. I mean, of course, you find certain unstable directions, right? This will destroy the dynamic stability, but it doesn't really tell you how many such directions exist. But also, it is weak in the sense you go from Kähler to Riemannian, right? So Kähler is very special, and indeed, if you because there was earlier result by Gantian and Xiaohua Zhu that if I still consider CPM with the Fubini studi, And if I only consider perturbations, but keeping the metrics Kähler, right, and Kählerity is preserved on the Ricci flow, then this Fubini Studi matrix on CPM is dynamically stable under the Kähler-Ricci flow. So somehow this non-Kähler is important. Okay. Let's see. Any questions so far? So far we've just looked at some like two notions of stability, right? And from now on, right? So what can we, I guess, say from Kröncke's result, right? So
Excuse
as I
me.
said, yeah, I'm sorry. Yeah,
Sorry, I have a
yeah,
comment. I have a question about the second remark.
yes.
Are there Kähler-Einstein perturbation of the Fubini Studi metric? Kähler-Einstein, are
Are
there?
these Kähler-Einstein or
Perturbations.
I don't think these perturbations are Kähler-Einstein, or maybe they are. I don't think so. I'm not sure. Yeah. So
Okay,
you're
okay.
asking whether these perturbations are still Kähler-Einstein?
No, whether there
Oh,
exist Kähler-Einstein perturbations.
oh,
So as far as I know,
I
the
I don't think
CPN
so.
is or Fubini Studi metric is isolated as an
Isolated.
Einstein
Yeah,
metric.
that's
Okay,
something I looked up. Someone ex told me this as well. Yeah, so there's no
okay,
Kähler-Einstein perturbation. Yeah.
okay, thank
Thank
you.
you. Yeah, no problem. And thank you, Paul, for helping out. Okay. Yeah. So I'll continue. So Krone's result, as I said, right? I think sort of clarified certain expectations or corrected certain expectations we have in this Ricci flow business. And of course, um, um, it also brings the question is sort of whether or not the subspace of Kähler matrix dynamically stable for a certain fixed point. And here I will include a remark. I think there's a result by Jeff Streets and Gantian. I forgot the year, but basically the space of Kähler matrix is stable under different flow. I think they define something weaker than a Kähler Ricci flow, but something called like a Hermitian curvature flow. Yeah, something between Ricci flow and Kähler Ricci flow. That's my quite sort of naive understanding. And of
Yeah, I
course,
think
yeah,
you need
yeah,
a flow that preserves the complex structure. That's why they
yes.
changed I mean, the Keller, the
Mm-hmm.
Ricci flow moves the complex structure if your metric is not Keller. That's why you need to
Mm-hmm.
change.
Mm-hmm. Yeah. And also this is just I guess as in some sense we Cronquist result says, okay, now I know this is unstable. If I follow this unstable direction, what do I see? And that's a sort of a natural question, right? So in the rest of the talk, I'll try to explain some of our investigation motivated by this question. Okay, so let's review some more for these thinkers, right? So far, right, in this talk, I've discussed a sphere. We've seen this cylinder, and this is another cylinder, and we've seen this. Now, if we have the S2 cross S2 with the standard product metric, if I perturb one of them just by slightly, say, changing the size of one, then I think it's not hard to imagine uh, you will form a singularity blow formed by S2 cross R2. You will also have so what else do we have? There's not much else we have here. So this is the everything. So this, let me put something. This is non-compact, and this is non-compact. Everything else, I'm sorry, yeah, this one is also non-compact. So we are here, right? So as far as the Kröncke's result is concerned, we are here with the Fubini study. Now, what Perlman's result says, so maybe it's better if I go to the next page. Here, let me go here and go, yeah. So because the shrinker entropy nu is monotone along Ricci flow and will only change if you go from and also if you run the Ricci flow, the monotonicity means it will only go from a shrinker of low density to high density, right? So if you go from let's say this is my soliton, and I perturb and I see some singularity, that singularity model will have a density higher in the list. And that's an example. Now, we are here. So the natural question is, if I perturb along the unstable direction, what do I get? Do I get something here? Even though I haven't explained what this is, or do I go to one of these guys, or maybe something we don't know yet? Okay, so our sort of catalog of the 4D shrinkers is summarized in this table, and yeah, we sort of want to know what's going on. Now, maybe some comments. In terms of the things in this table, the top in the list is just a R4 with a flat metric. Now, you might but you can also put how should I say? You can add a vector field to rewrite it as a sort of a so-called Gaussian shrinker. So you can still realize it as a shrinking soliton. So yeah, and you can prove it is in fact dynamically stable. And we just saw the sphere is dynamically stable. And we saw by Kröncke's result, CP2 with Fubini study is dynamically unstable. And I explained S2 cross S2 with a standard product metric is dynamically unstable. And then these three, yeah, I think they are still conjectured to be dynamically stable. Yeah. So these guys remain in the list. Now, so what is this? So this FIK deserves some comment here, right? So this is an example of a complete shrinking Ricci soliton on CP to blow up the origin. So it is in fact a Kähler shrinking Ricci soliton. And there's a reason, or maybe in fact, well, there's a sort of a conjecture that if we perturb the complex projective space, or CP2 with the Fubini study in this unstable direction, it will form a local singularity modeled by this FIK. Okay, so that's the expectation. But we can't prove it yet. We have some evidence for this. So let me now explain sort of our analysis to see this evidence. So from now on, we'll be focusing on CP2. And then on this, we'll be considering U2 invariant metrics. And the way we think of them as basically on an interval, I put S3 fibers, except at two ends, they degenerate. Now, this is in general Riemannian, or of course, I can also hide this row variable and make it into arc length. So for either G written this way or this way, it's important to know that this metric will be Kähler if and only if the f and the function f and the g here, they satisfy this relation. Okay, so this is a useful fact for us to check Kählerity. And with this setup, all we're going to do is we basically want to study Ricci flow starting from a metric of either this form or this form. Okay, that's what we're going to do now. And of course, whether I study the Ricci flow for metric written in this way or this way, it's a matter of studying a system of PDEs, right? A PDE system for the function either f and g or f, g, and rho. Now,
So Haotian,
yes,
what
yeah.
happens? I mean, there must be some non-trivial sort of matching conditions for smoothness, right?
I will put them later. Yeah, I will put them later. Yeah. At this stage, I haven't said anything on the boundary, but yeah, they will be important. In fact, I think that's one of the sort of the difficulty, maybe analytical sort of analytic difficulty. Yeah. Okay. Yeah. So, the Fubini-Studi matrix is very explicit in complex dimension 2 or real dimension 4, right? So the rho function is identically 1, the f looks like this, and g looks like this. And this unstable perturbation, it turns out to be also very explicit. It can be written like this, namely, I have a conformal change of the Fubini-Studi metric. And it's not hard to check that this G naught does not satisfy this equation, therefore it's not Kähler. And now, like Ramiro said, okay, well, I'm not there yet, but I'll get there. So if I choose to keep track of the rho and f and g, these three functions, then I get this system. These two are okay, but this one is not so nice, and the whole system is not parabolic. But this is not a sort of an essential difficulty because we can, for example, work in the arc length coordinate and thereby working in this gauge, and you get a parabolic. You fix the ellipticity on the right side, and then you get a parabolic system of PDEs. And then for this f and g, and to close up in the right way to induce a smooth metric on CP2, we need to impose the following boundary conditions at two ends, at theta equal to 0 and theta equal to pi on 2. So that's the thing Ramiro asked about. But this means we have an overdetermined PDE system. And this is, we don't know how to do that. Yeah. Now, yeah. Another way is so here we just choose to work in the arc length coordinate, right? Alternatively, you can also apply the de Turk trick to the Ricci flow. Namely, I add some diffeomorphism term to the Ricci flow equation. And here this x can be generated by you fix the background metric just to be the Fubini-Studi on my CP2. And I take the difference between the Christoffel symbols of my evolving metric G and the Christoffel symbols of this background metric, and I can generate a X like this. So somehow what I want to emphasize is this is one way to fix the the lack of parabolicity in the system. But there's an alternative way, right? Just apply the de Turk trick. You can also fix the lack of parabolicity in the system for rho and f and g. Of course, the price you pay is you get this, okay, you see this now is good, but this system looks pretty ugly. And also, we still haven't sort of bypassed this overdeterminedness in the boundary condition. Okay, so at least, so what I mean, okay. So the way to put this is, there turns out we eventually found a trick to hide the boundary conditions, and the detail. Okay, so maybe the punchline is instead of considering rho, f, and g we consider functions a, b, and c, right? So basically we have, and it is enough to impose Neumann boundary conditions for a, b, and c at two ends, and we somehow fit the boundary condition. And the price we pay is we get this very ugly system. We just don't know how to solve analytically, right? So I mean, not even like analysis. So this is not too satisfying. But what we could do is we could maybe sort of understand this PDE numerically. And here the numerical scheme is very standard, right? You just do the space difference quotient in the space variable and do the standard Euler method in time variable. Now at least for this the system of these three equations, what we could find numerically is that if I take the Fubini-Studi metric and perturb it using our conformal perturbation, then I run the Ricci flow, then the Ricci flow will develop a type 1 singularity at one of the ends. And of course, we see this numerically, we don't prove it. And now if we know it's a type 1 singularity, and we are also in dimension 4, then we know the singularity model should be some kind of a gradient shrinking soliton. And the next question for us, again, in this numerical investigation is, how do we recognize our solution, right? And in particular, the soliton here. And we will, in fact, we could, again, numerically, maybe get some evidence for the soliton in the sense, first, we saw the metric is becoming Kähler. And second, the metric is approaching the FIK soliton. Okay, so let me see. Any questions so far? Okay, so how do we see the matrix Kähler? Well, this is essentially, numerically, we can keep track how this quantity evolves. And it's not too complicated. Now, we in fact realize that I think the complex structure has an opposite, is flipped at the singular time. Now, the next one is maybe more interesting because how do we recognize it's the FIK? That is because the FIK soliton is a shrinking gradient Ricci soliton, which is asymptotic conical. And the result by Koshwa and Lu Wang says that given any cone, there's at most one shrinking gradient Ricci soliton asymptotic to that cone, right? And the FIK soliton itself, even though you don't really compute it explicitly, I mean, okay, you can't write down it in a very explicit way, but it is possible to compute the asymptotic cone angle. It is given by 1/√2. So again, I mean, we can solve f and g, right, numerically, and then we could sort of see it approaches this cone angle. Okay, so basically, with these two considerations, we found some numerical evidence in favor of this conjecture, namely the 4D Ricci flow starting from unstable perturbations of Fubini-Studi metric will form a type 1 local singularity modeled by the Kähler FIK. There were sort of two remarks, right? So first is our result is consistent with a result by Max Gdolowski, which says the FIK soliton will appear as the type 1 singularity model of some Ricci flow. Okay, I mean, I think in Max's sort of proof, he didn't say which manifold, but he was able to show any asymptotic conical shrinking Ricci soliton will show up as the type 1 limit of some Ricci flow on some closed manifold. And the second result is very recently, this very substantial work by Knopf and I think Knopf and Ozuk. They prove that the real dimension, in real dimension 4, right, the FIK soliton is in fact variationally stable. Okay, so this is very, that's a very long proof. And of course, the question is, you might ask, does this further imply the FIK is dynamically stable, right? Whereas somehow our result is a bit different in the sense if you go back to the table of the, but related, right? If you go back to the table of the here, right? I would like to sort of think is you should expect stability of this FRK now, given the variational stability. But then what we show is you perturb here, it will eventually go there. Yeah, so not precisely the same thing. Yeah, but I think maybe with this new big result, we might get some new insight in this system. And of course, our numerical sort of work also give you some evidence in the sense you have one example where you have a Kähler metric, you perturb, so the perturbation is no longer Kähler, but on the Ricci flow, it still sends the metric towards becoming a Kähler metric. So it gives, again, some kind of evidence of this. Maybe it all is related to the question of stability of the subspace of Kähler metrics among, let's say, Riemannian metrics, right? Okay, so yeah, I think maybe it's a good time to stop here. And then thank you very much for your thank you, for attention.
Thank you, Haotian, for a very nice talk. Are there any questions for the speaker or comments?
So I have a question.
Yeah.
Yes. So these unstable directions for CPN, as far as I know, so you said they are conformal changes of the metric. Right?
Yeah. They are pretty. Okay, so one set of such conformal change can be written down explicitly, but as I said, I don't know if they capture all the unstable directions. Yeah, but sorry, let me, please finish your question. Yeah.
That was going to be, more or less my question.
Okay.
As far as I know, you have these conformal. So the functions you take are eigenfunctions to a certain eigenvalue.
Yeah, that's correct. Yeah.
Operator.
Correct.
And you're picking one eigenfunction which is U2 invariant, right?
Yeah.
And then you see what Ricci flow does.
Yeah. All these in this case, the perturb guys, they're still U2 invariant. Yes.
So it could be that if you pick another eigenfunction, you would get a different limiting behavior.
Yeah, it's possible, but do you still do a conformal change like this? Then or do you do something else?
It would be something which is not invariant, not U2 invariant, right? So
I see.
You would lose your homogeneity, so probably it'd be hard to do. But I think, if I read Kröncke's paper correctly, that you cannot just pick any eigenfunction. You have to pick someone.
No. It's not any particular, and this is one you can pick.
Not vanish.
That's correct. Yeah, you have this some condition which forces the third variation has a sign. Yeah.
Yeah. Right.
Yeah. But
Okay.
Again, somehow I think it's the set of sort of unstable perturbations you can write down is sort of sort of encoded in this non-vanishing condition, and you spell that out. I think this is one set of perturbations you can do. Yeah, I see. But I see you saying maybe there are some other ones. Okay, maybe we can consider that. Yeah.
Okay.
More
But
general
maybe
perturbations.
it also already is the generic eigenfunction in a sense, because there can of course be different U2s corresponding to different. You have many different conjugate U2s acting on your CP2, right? So each of those would give you a different set of U2 invariant eigenfunctions. Maybe these are already almost all eigenfunctions of that eigenvalue. I'm not sure.
I see.
But yeah, I think the one for which the integral does vanish would be probably a bit unclear. Or do you have an idea what?
No, I don't have a very clear idea. Yeah, I don't have a clear idea. No, yeah.
Yeah, but I must say it's already amazing that you can do it for.
No. Yeah. Sorry.
It's great.
You were.
I know. It's just a comment. I must say it's really amazing that you can do it for this eigenfunction.
Yes.
You can convert it from. This is really.
Yeah, but we can't really. analyze it. I mean, that's the silly part. I mean, let me put a comment because I mean, this is not the first kind of paper on non-rotationally symmetric reshuffle. I think by now there's a lot of you impose a stronger symmetry. You can do some analysis because the PDE is just a single PDE, right? But I think let me just write a comment here. I think Isenberg, again, Dan Knopf, and Natasha Sesson. What they could do is they could study on four manifold. Again, writing it as a sort of a S interval cross S3 closing in the right way. They can impose sort of a non-rotational symmetry, but still study a system of PDEs, and somehow in that context, I think they could show the formation of a type 1 singularity modeled by the neck, which is S3 cross R. Yeah, so here is somewhat a slightly different business. Yeah, so
interesting.
So somehow the analysis, and this is a paper I think in like CPDE around 2016. Yeah, so let me actually I have to say, I mean, yeah, I'm not too good at the group action. Ramiro would know this. He gave me a crash course on group actions, but I hope to learn a bit more than like Paul, you said. Yeah, so somehow to understand the maybe the interaction between the group actions and the PDEs, maybe that will give us more information. Yeah, I don't know quite yet, but I want to say there is some other work in the context just purely a PDE system where Maximus principle doesn't work, and you probably have to cook up something that works. So yeah, but somehow it worked in this case, but we haven't found a good way for it to work in this particular problem. Yeah, which when we resorted to this very ugly stuff, but I don't have anything better to say at this stage. Yeah.
It's still very nice. Yeah. So thanks for the answer.
Thank you. Yeah. Thank you. Yeah.
Any other questions for Haotian? Patrick, go ahead.
Yeah, so can you hear me?
Yes, I can hear you.
Yes.
Yeah, okay, perfect. I was just wondering, so there's, the U2 action gives, different closing conditions on the different ends of, CP2. I was just wondering, so one of these ends is a point, I believe, and the other is like a CP1.
Yeah, that's
And
correct.
so
Yeah.
So one of these you get, like asymptotically conical from, what we expect to be the FIK shrink here. But do you think there's like a possibility, you could get, some strange conditions on the other end? Because like if you do a perturbation of the Fubini studiometric, we probably aren't going to see any, singularity models on the interior, but on, is there a possibility we could have like, something strange acting up on the other boundary, I guess is what I'm saying.
Yeah, so short answer is I don't know, because if everything is strictly Kähler, then you can check maybe things are easy. But since now this is, I don't know, at least for this particular example with like you said, right? This just this is really strictly CP1 at the one end gets crushed and you blow up, you see asymptotic conical. Do you mean you put a different boundary conditions here initially, or no?
Oh,
Maybe
I mean,
I'm
then
misunderstanding.
then
After
you'd have a different
perturbation,
metric.
you mean? Yeah, or
Yeah. So
or
after perturbation, wondering if you could have
no,
something else.
but I think, but for us, we still have the same boundary conditions for even after the perturbations, right? Because somehow these are the fixed boundary conditions throughout.
Yeah, but I guess
Yeah.
what I'm saying is like,
Mhm.
in this case, you're expecting, a singularity model to appear on, somewhere on the orbit space. And, I mean, in this case, the fact that you get the one corresponding to, a point and it goes to Kähler, I think probably automatically gives you that it should be the FIK shrinker. because it's cohomogeny 1 with U2, whatever. But like I'm wondering if, you know, because you see this analysis of, you know, neck pinches and so on, where you get like, you know, something in the middle, or, you know, maybe in this case, because the ends are different, you could have something interesting happening on the other end, I guess is what I'm saying.
I think there's also the fact that he is rescaling at the points where the curvature is maximum, right? So the point picking argument to see this type 1
Yeah, because
the
somehow
shrinking
I
gradient
think
soliton.
you can
But the
argue.
question whether there's it could be other tangent flows, of course, right? So maybe that's more what Patrick is asking.
But yeah, so I mean, regardless, are you expecting in the general case, you know, this dynamical stability of, you know, kind of the Kähler subspace of metrics as well, in general?
So in general, I'm not sure, because I think again, there aren't too many examples of so let me go back to this table, right? So somehow I think there aren't too many. Okay, there are many fellows down below, but they're unstable and they're Kähler. But somehow above CP2, I don't think there are many examples. So maybe this is generically what you can see or something. I'm not being, I might just be speaking nonsense at this stage. Yeah. Because somehow, like, suppose you want to see something else, what do you see, right?
I mean, S2 times R2,
But
this
these
is also,
normally are in the middle, right?
yeah.
I don't know. Normally these
But
are in the
I
middle.
guess
So
what I'm
yeah.
saying is, like, you know,
Yeah.
if you have like a CP1, maybe you could get something strange like that, but I don't know.
Yeah, but CP1 is S2, right? So I don't know.
Yeah, this is what I'm saying. Like, you know,
Yeah,
maybe you can get
so
some non-conical thing. I don't know.
All
Or
right,
I
maybe
guess
we
the
can
U2 symmetry.
continue
Anyway.
the discussion
yeah, Patrick, you're local, so we
after.
can continue after.
Yeah.
Yeah.
All right, let's thank the speaker again for a great talk.
Yeah. Thank you, Lauren, and thank you everyone for your questions. Yeah. Thank you. Nice meeting you all.